Hey guys, I got a special episode for y'all today. I was contacted on LinkedIn by the CEO of Threshold.ai. He wanted to know if I wanted to tear down one of their quantum computers. Of course, I said yes. Only catch is either I had to go to the quantum computer or the quantum computer had to come to me. And so here I am in sunny San Francisco. Thank you. Alright, so it's going to take about 5 minutes to calibrate. Calibration will be performed automatically later, so you can cancel this procedure. Alright, so we got the screen to start up, and yeah, device disconnected. Okay. Alright, let's try this again. So when you're starting it up, you can hold down the push button, the start button, and then don't let go of the start button until both you hear the fan noises and the screen comes up. And then you'll see something like this. Allow USB to serial converter. That's probably a yes. And there we go. We're at the start screen. All right, so this is the home screen. You got about 8 options to pick from. And they call this program Caster. So in the lecture section, it's got a bunch of slides. I would say you probably need at least some college to really understand it. A lot of propaganda. And a little bit of broken English, not terrible though. Overall, I think it's pretty nice. It's a good review before you really get into it. And then it also has stuff to kind of teach you how to use the machine. So overall, I would give it about a 9 out of 10 with rice. It's a bit scattered, kind of like it was made by a bunch of different people. Without much, conglomeration at the end. But if you search for it, like if you have a question about a different part, they tend to answer the question somewhere else. So like they have a pretty in-depth introduction to linear algebra in case you forgot those basic concepts. So the slides have kind of links to the exercise questions, so you kind of test your knowledge as you go. And yeah, another cool thing is at the end of a lot of chapters, they kind of go into the Caster software and how what you just learned applies to what you can do with the system. So in one of the chapters, I guess lecture 14, they talk about how to make a quantum computer, and they basically give you the outline of this circuit. I guess technically they're giving you the outline of the old Gemini, because this one, instead of connecting to a PC with SpinQuasar, they connect to a tablet with Caster. But other than that, it's basically the same thing. You've got the FPGA, which is kind of like the microcontroller, and it does the listening and the talking, and has to be an FPGA because nothing else is going to really talk to the atoms at the rate that they need to be talked at. I mean, you're going to be sending signals at like, what is it? 67 microseconds. So yeah, you've got some pretty quick maths to do there. And yeah, you got the 2 magnets. The control and detection coils are a bit smaller than I would expect, but again, I don't really know what happens at that kind of frequency. Maybe you just don't need that much stuff. And you got the shimming coils, and yeah, a bunch of the electronics, which lets you smooth out the signals and talk to the machine better. In the next slide, they kind of talk about the order. So the computer's like, hey, I want to send an H gate on the first qubit, and then the FPGA converts that into a signal, sends that over to the digital to analog converter, that then amplifies the signal and then sends it over to the qubit, and then it tells you what happens in reverse. Basically, the transceiver antenna listens to it, amplifies the signal, sends it to the ADC. Then that signal is converted to something that can be sent over serial to the computer that the computer can understand, and then it tells you, in a human way what happened. So you can ignore this one. This is a 3-qubit system. That's not what we have. We have this dimethyl phosphite, and you can see you've got your phosphorus 31. Statistically it's 31. So if you look at the atomic mass for phosphorus, it's like 30.9. So, you know, it's kind of like 90% of the time you're going to have the right amount of neutrons to make this a spin 1/2 phosphorus. And then you get the hydrogen, and in the spec sheet, it tells you the, you know, at the magnetic field, you got a Larmor frequency for the hydrogen at 27 and for the phosphorus at 31 megahertz. And so, yeah, you can, you know, send different signals to each atom. And so with a multi-qubit system, you also have this J coupling strength, which is, you know, hard to explain at a glance. But basically, it's kind of like the energy of the two qubits talking to each other. And so that's kind of like the signal that you'd have to send or listen for when you want to have inter-qubit operations. So the next button to press is this course exercise button. And they've sort of kind of gamified the learning experience, which, you know, everyone loves unless you're trying to get through things quickly. But yeah, you just kind of click on a constellation, and then you click on a thing, and a star, and you got a question. So here it is, quantization and continuity of physical quantities. Whether the following physical quantities are quantized or continuous, please choose the correct one. So a little broken English, but I understand. Electric charged. That's probably quantized. People, I don't think you want half a person. Length, and that one tends to be continuous. Cache, ooh, that gets tricky, but I'm gonna go with quantized. And then color tends to be continuous. Okay, let's submit. See how I did. Perfect answer. All right, I'm feeling good. Got that hit of dopamine. My star lit up. So as a physicist, this next part is probably my favorite, simulation training. And so let's just set up a quick example. So normally it just says 1 qubit, so you can press up here to go 2. We'll set up a Hadamard gate. So a Hadamard gate, basically what it does is it takes your qubit and kind of goes halfway, only spins it halfway. But if you understand qubits, you don't have a halfway. What you have is like a superposition of up and down at the same time. So it basically splits that probability into up and down. And so then you can have a C0 gate on the second qubit. Hopefully you guys can see that. And then you got to click up to tell it which qubit to C0 with. And so basically what that means is that now this qubit down here at the bottom is reliant on what's going on at the first qubit. And since the first qubit is split, then that means the second qubit is also going to be split, and that ends up entangling the two qubits into a system that can't be unentangled without, you know, decohering it without observation. And so then in order to actually, you know, look at the probabilities, you go up here to simulate, and then it does some thinking, and then you got to click up here again, and then you can look at the probabilities. And as you can see, we've got 0, 0, and 1, 1. So what that means is that there's and here it says 0.499, so we got some computer errors up here, or you know, computer arithmetic, rounding errors. But yeah, basically it's got a 50-50 probability of either they're both in the down state or they're both in the up state. But you know, they're entangled. They're both. If you find that one of them was in down state, you instantly know that the other guy is now in the down state, or always was. I don't know, depends on your quantum philosophy right there. What's cool about this is that if you go to their website, SpinQ, I'll try to have it links down below. You can actually access this trainer for free, the simulator, and you know, play with it all you want. And it's actually kind of better because in that one you don't have to click simulate and current task and all that stuff. It's just you put down the gate and then boom, you see all the probabilities. On reboot, I get this device calibration screen. It says, in order to ensure the device runs better, it will take about 5 minutes to calibrate. Calibration will be performed automatically later, so you can cancel this procedure. After 25 seconds, the calibration starts automatically. Let's just start it now. So after about 5 minutes, the shimming cables set up the magnetic field so that all the nuclei can dance together, and we got a good peak. And then we got device connected, we got process 100% idle, current status idle. Yeah, everything's looking good. The auto-shimming section is probably the most interesting to me. Um, Looks like they've got 13 shimming channels, so basically probably 13 sets of coils all around the surface. And then they give each one a different voltage, and they probably have a shimming algorithm. This is one of my bigger questions that I'm still trying to find is what kind of shimming algorithm do they have? It's probably some sort of gradient descent, but it'd be cool to know exactly. Their archive paper just says a full width half max algorithm, but that doesn't really tell me anything. That all that's saying is that the width of the peak got smaller. The next one, the lock field, is pretty cool. Basically, what that's doing is it's kind of constantly running, the one qubit NMR experiment, and basically it's so that it can tell, because as the temperature changes, the way magnetic fields work is you've got like the little poles inside of a magnet, and they're kind of they like to line up, and then the fields kind of go out of the north and into the south, or whatever philosophy you subscribe to. But you can imagine that if temperature means like shaking is happening with the little magnets, and if it's shaking a lot, then they're not lined up as much. And so what that means is that the higher temperature you have, the less of a field you have, and with this kind of a system, you want to be as precise as possible. And so what the lock field is doing is it's constantly running the experiment, and it's saying like, okay, the temperature must have changed because I'm not, as lined up as I used to be. This peak isn't as good as it used to be. And so I like the lack of units, just amplitude. And so the shimming magnets are probably changing to make sure that it doesn't, go too far. Basically, it increases the magnet power or decreases the magnet power as necessary. In user settings, it's kind of what you'd expect, language, Wi-Fi, remote connect, update, just general updates, restore parameters to factory settings, and then about caster device ID, about SpinQ, and some information. So I'm not sure if there's a way to change the brightness settings through the caster code, but in the end, this is a tablet, and so you just kind of have to keep trying to get it. Okay, there we go. And then, like any other tablet, you just kind of slide over the brightness, and hopefully that'll make it easier for you guys to see. Okay, with all that out of the way, we can go into quantum computing. There is my tasks, but it's basically like if you made a simulation that you like, you can save it and then go there and find it later. Or by simulation, I mean, a procedure that you like. You can load it up in my tasks. So yeah, I was just kind of trying some random stuff, just so you guys can kind of understand what's going on. So I'm going to do a x, square root of x operation with x, y, z. We start up in this, pointing in this direction. And so a rotation about x means that we're going to like move from here to here, right? And like we should be pointing negative y. But from the z coordinate frame, this corresponds to, remember, we can't do halfway. We are both we're halfway up and halfway down. We're both up and down. So that's what we should expect to see, is a vector pointing in the negative y direction. So I'm going to hit run, and we're doing some, I guess you could call it quantum mechanics. It's it's one qubit, so it is quantum mechanics. I don't know if you could call it quantum computing yet. We are doing 1 qubit manipulations, and we're at 14%. So let's give it a minute, and it looks like it's finished. So let's go up here to current task, and there we have it. So it looks like it might have overshot a little bit, but you can see how we started out in the z direction, and then we rotated about this x guy down to here. And so now, these should be even, but it's the real world. We don't always get the theoretical perfectness. All right, now for some real quantum computing. Let's set up a squared, actually let's do the real one. Hadamard with a C0 gate, and we should get entangled, and we should see a 0011 state. Let's try it out. And it says it's finished. Let's check it out. Uh-oh. Apparently we got nothing. Okay, let's try it again. So one nice thing is that we've got some examples. You got to go up to case, and let's just do something simple. I want to get into the 1-1 state. So both qubits basically flipped. And let's run it. That's odd. I'm getting nothing, even from their examples. So I followed the example in the manual. Just kind of set up this operation, and it says I should be expecting 1/4 of everything, but instead I get nothing. So I noticed that if I do a factory reset and then just kind of calibrate it, just go through the calibration steps manually, it seems to give me some results at least. Although, okay, so if we have Q0 and Q1 initialized at 0, and then I do a 180-degree rotation for both of them, I would expect to get 1-1, and the higher 1-1 the better. That's what the simulation also tells us. But looking at these results, I get 50-50 on everything. So yeah, something is still very wrong. So the quantum computer comes with a basic operations manual, but it's like 10 pages long. I wish it came with a complex operations manual that kind of explained everything. I checked the website and I couldn't find anything there. The closest I found was the archive preprint paper that they published about the Gemini system. All right, so this is the quantum computer with the lid off. I believe this test tube looking thing right here is the sample. What's weirding me out a bit is that the sample is kind of like an orangish color, and then like this part is kind of orangish, so hopefully none of it's leaking. That'd be kind of scary. Dimethyl phosphite is level 4 flammable, level 2 carcinogen, level 2 mutagen. So I'm going to try to be as safe as possible. While we're here, so it's kind of hard to see, but if you look closely, you can see there's kind of like Q right there. It says Q spin, or maybe Q spin Q. But those are the shimming coils. And it looks like they're in kind of like a stacked PCB format, which kind of makes sense. PCBs can get pretty specific with the copper routing. So you can just kind of like, there's 13 channels and you could probably cram all of them in there. I believe these two outer cables go into the transceiver antenna, which, surrounds the sample. Then it looks like there's metal discs on the outsides. Those are probably the magnets, the here and here. And then it looks like rubber maybe on the outside of that, and it's probably for dampening. And then, yeah, this whole thing's in a case. One thing that concerned me is that, this thing was kind of loose, and it looks like the plastic tabs have snapped. So that's probably going to reduce the noise, because when something has a case like this, it tends to be for temperature, to keep the temperature as steady as possible. And my guess is that all the thermal cycles, like the plastic didn't like the fact that this thing warms up, cools off, warms up, cools off, so the plastic's expanding and contracting, and I'm guessing at some point they just snapped. So if I were gonna pour material into this kind of device, I would probably put some sort of test tube looking thing that looks like a cap on it. Two, because dimethyl phosphite oxidizes into phosphine gas. They're both colorless, but when phosphine gas accumulates on a surface, it turns orange brownish, which that looks orange brownish to me. And then three, so like it's denser than air, so it kind of makes sense that any stuff that's leaking wouldn't really stain the outsides or like the top of the case, but the outsides of the case also look orangey brown. So that makes me think that maybe some of it did leak and is staining the outsides. Over on this side, we have a bunch of high wattage resistors and a bunch of transistors. And so the way this machine works, so earlier I talked about how the magnets need a steady temperature, otherwise the magnetization changes slightly, and there's physics reasons for that. And so in order to keep this temperature steady, instead of trying to cool it and heat it at the same time, they basically just heat up the device and then they just maintain that temperature above the ambient temperature by just heating whenever it starts to cool off. So that's pretty cool. So like I previously stated, those blue cables come in from the transceiver coil and go into this PCB. It kind of looks like my PCB, where it's just a chain of op amps and resistors and capacitors. It will probably do the low pass filtering and the other cleaning and amplifying of the input and output signals. From there, you move on to the main, I would call it the motherboard. Underneath that, right here, this black heat sink, I'd be willing to bet that's where the FPGA is. You need an FPGA because the frequencies are so high. It's hard to, like an Arduino has okay, so the Pi Pico has 48 megahertz as a signal rate, and like the signals that this device wants are in like the megahertz range. So there's no way like a Pico could do this. You need to have like, devoted hardware to launch signals at the speeds necessary. And so that's what this FPGA is for. And then, I don't know, there's another microcontroller there. It's probably just for communications. Because then at that point, we've got one of these black cables. I don't know if it's this one, but it goes all the way around and then it comes down here. And then that's what communicates with the tablet. And then finally, you've got what I believe is the power supply, which takes in the 12 volts and just changes it to whatever the circuit needs, 5 volts, whatever. So I'm torn. I really try to like this computer. I mean, after all, it's the future. It's a piece of magic in the form factor of a scanner that you can keep in your house and play with it whenever you want. You can wake up in the morning and be like, hey, I want to try this quantum experiment, and boom, 10 minutes later you're a physicist. The problem I have with this quantum computer is that it tries to be the Apple product of quantum computers. It gives you this big button as soon as you start it up, and it's like, hey, click here for quantum magic. And the problem is that it's not Apple. It doesn't have, like when your Apple product doesn't work, you take it down to the Genius Bar and they fix it, or they don't fix it and they charge you a bunch of money, and you either get a fixed phone or a new phone. And you can't do this with this SpinQ. There's I saw there was a Copilot function, so someone could theoretically log in and try to troubleshoot it with me, but it didn't really tell me how or where to get someone to do that. I contacted the support and they basically told me turn it off and on again. So yeah, I have a problem with that. I understand if it's not going to work, that's fine, but the device should know that it's not working. It should be like, hey, I gave you nonsense, watch out, here's an error code. And then I can take that error code and give it to support and they can help me troubleshoot it, not oops, nothing happened, I don't know why. I'm not sure about dimethyl phosphite. It's in some parts of the manuals I read that it was like 97% pure. In some parts it says 1.5 parts per million. I don't know. Either way, if it was pure, if you drink it, all of it at the same time, and you were a mouse, or a human the size of a mouse, no, the other way, a mouse the size of a human, you would increase your chances of having like liver and lung cancer by 1 in 150. So, any amount of like small amounts of gas that are escaping, it's probably no worse than walking through a polluted city. That said, in the safety manual, it talks about the dangers of having like a pacemaker around these magnetic fields. You'd think it would give you, some sort of like warning, like do not disassemble, or like warning, dangerous chemicals, dispose of properly, something like that. All that said, seeing this machine makes me hopeful. The scientists at SpinQ are pioneers, and soon there's going to be other companies with cheaper, smaller, better quantum computers that anyone can purchase and learn from and tinker with. Even this particular model, the Gemini Mini, is the second iteration of the Gemini series. And it's smaller and it's got the tablet, easier to use. And this, the same company, SpinQ, has already come out with a third quantum computer, the Triangulum, which has 3 qubits and has way more research potential and customizability that kind of shows me what kind of future we could be living in. Until the day comes that I can go down to Best Buy and pick up one of these for cheap, I am going to keep working on my design, and I'm going to keep trying to make it easier for people to use and to learn from and to build their own. Until then, stay crunchy.
Boop, 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 boop.
The D-Wave might be impressive, but can the D-Wave run Doom? Get some quantum. Shoot, how do I turn? Oh jeez. Oh jeez. Yeah, die quantums. Die. Pew 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 pew. Pew pew pew. Alright, good health pack. I definitely need that. I almost died. Can't lose no quantums. Get some. Get some. Yeah. Yeah. Who's the quantum now? Do 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 ba do ba do ba do boo. I don't think that's a song. Oh, my character's not looking so good. I have to change the rating. How do I open? Alright, I did something. Elevator. Oh, jeez. Oh no, I can't take those. No. No, save me, Jeebus. No. No. Good game.